You might think engineering is all about nuts and bolts, about making things work. But sometimes, even the smallest design choice can have consequences that ripple out in ways you'd never expect, sometimes with truly devastating results. Let's dig into one of those decisions. So, picture this. It's August 10th, 1978. On a highway out in Indiana, a Ford Pinto gets into what should be a pretty routine kind of accident, a rear-end collision.
But in just a split second, what should have been an ordinary fender bender turns into an absolute catastrophe.
See, the impact itself wasn't the deadliest part of the crash. It was the fire that came next.
A horrific human cost. And what's really chilling is that this wasn't some one-in-a-million freak accident. In the years leading up to this, there had been about 50 other lawsuits related to Pinto fires from rear-end collisions. This wasn't an unforeseen flaw. It was the result of a very deliberate, calculated decision. Ford's own engineers knew that the fuel tank's placement was incredibly dangerous. But it was a design that saved on manufacturing costs. The company had prioritized getting the car to market fast and cheap over safety. This whole tragedy really brings up a fundamental question, doesn't it? When an engineer's core duty to protect the public is in a head-on collision with their duty to their employer, how are they supposed to navigate that? What's their guide? Well, there's actually a whole field that grapples with these exact dilemmas. It's called engineering ethics, and it's the framework for making these incredibly high-stakes decisions. So, what is it really? At its heart, engineering ethics is the set of rules and standards for how engineers should behave as professionals. It's not just about technical skill, it's about moral responsibility. And it's really important to draw a line here between this and our personal day-to-day ethics. I mean, being a good person is the foundation, of course, but professional ethics is a whole different ballgame. It deals with these huge, complex organizational choices, like balancing public safety against a multi-million-dollar product launch. But what happens when the choices aren't so black and white? When it's not a clear case of good guys versus bad guys, but about good, important principles that are in direct conflict with each other? The range of issues engineers have to deal with is just massive. We're talking about everything from obvious no-nos like bribery and fraud to much fuzzier areas like environmental protection, fairness, conflicts of interest, and maintaining honesty in research. It's a lot to juggle. I mean, think about it. The choices an engineer makes can ripple out and influence business practices, public health, even politics. That is a huge weight of responsibility on their shoulders. All right, let's turn to another case study. This one's even more complex, and it's a story many of us know, the story of the Space Shuttle Challenger. The pressure to get this shuttle off the ground was just immense. NASA had faced a ton of delays, and they desperately needed a successful mission. There was even political pressure to launch before the president's State of the Union address. And at the heart of all this pressure was a very specific, well-known technical concern. It was all about these rubber O-rings. Their job was to seal the joints on the giant solid rocket boosters. The problem? Everyone knew that in freezing temperatures, that rubber could get brittle and fail to create a proper seal. If that happened, hot gas could escape with, well, catastrophic results. The data on this was pretty stark. The absolute coldest launch they had ever attempted before was at 53 degrees Fahrenheit. And even then, engineers had noticed some erosion on the O-rings. The forecast for the Challenger launch was 29 degrees. I mean, that's so far outside of any existing data or experience, it was completely uncharted territory. So, the night before the launch, the engineers who actually designed these boosters, Roger Boisjoli and Arnie Thompson, gave a long presentation detailing all of their concerns. Their recommendation, which was fully backed by their own vice president of engineering, Bob Lund, was crystal clear. Delay the launch. Wait until the temperature is at least 53 degrees. But NASA officials pushed back hard, arguing the data wasn't conclusive enough. Then, in a now infamous moment, a senior manager at the contractor company, Morton Thiokol, told his VP of engineering to take off his engineering hat and put on his management hat. Under that intense pressure, the recommendation to delay was reversed. The launch went ahead. You could see puffs of black smoke almost immediately, a clear sign the O-rings had failed in the cold. Just 73 seconds later, the world watched in horror as the shuttle disintegrated in the sky. This disaster wasn't really an accident. It was a systemic failure.
It was a failure of communication, a failure to respect the boundary between sound engineering judgment and management pressure. It's a textbook case of what sociologists call the normalization of deviance, where you know there's a flaw, but you keep accepting the risk over and over again until one day it leads to catastrophe.
Okay, these stories are grim, I know, but they offer a really powerful lesson. If we can engineer something as complex as a space shuttle, can't we also engineer a better way to make decisions? Well, the answer is yes, and the process is actually surprisingly familiar.
The key is to treat an ethical problem just like an engineering design problem. First, you define the conflict. That's your problem statement. Then you gather all the facts, figure out who all the stakeholders are. That's your data gathering. Next, you brainstorm multiple courses of action, just like designing alternatives. And finally, you analyze each one and choose the most ethical solution. It's a systematic process, not just a gut feeling.
And the real goal here isn't to just memorize a rule book. It's about cultivating what's called moral autonomy. That's really just the skill to think for yourself, to critically analyze these complex moral problems, and to navigate the tough choices with integrity, especially when you're under a ton of pressure. As technology gets more and more powerful, from the cars we drive every day to the AI algorithms that are shaping our world, the decisions engineers make have never been more consequential. So the real challenge going forward isn't just about building better things. It's about building better ways to decide what things are worth building in the first place.